don't miss it. Great. For today, we have Professor Popescu from IHE Delft as our keynote speaker. So be very, thank you, Ioana, for being with us and accepting our invite. We are really grateful for your agreement to our invitation. So, Dr. Popescu, are you ready to
yes,
share?
Yes, I'm ready. Yes. Shall I share the screen? Thank you very much, Vidya.
Yes.
Shall I share? Yes, I can.
Let me check the setting because it goes a little bit off sometimes. Yes, I think you should be fine. I just clicked it. Yes.
Share. And I will need to make it in a. I hope that it is visible. I will need to move this from the. You can see it. Thank you very much for the invitation. I'm privileged to be able to tell you a few things about our work at IHE. So the title of the presentation for today is the Hydroinformatics Approaches to Flood Modeling, Challenges and Solutions. And everything that I'm going to present is not done as one person. So it is things that we are working with our student and with special contributions of my colleague Andrea Ionowski and of our PhD students that are here. So let's see, it doesn't advance. Yes, it advances. Yes. So just very shortly, a few words about the flood research that is done at IHE in many groups. But if I think of what we have done in the hydroinformatics group in the last 20 years, we have been looking at flood problems in many countries. I can list many rivers, 30 basins, also in lakes within projects and with our MSc and PhD students. And to acknowledge many projects in which we have applied floods, I am not only showing you where in the world are these case studies, but also the projects in which we have been involved. And actually, I have selected for today to show you some case studies in projects that are listed there. And we have used many tools for different case studies. From hydroinformatics point of view, we look at case studies from many perspectives, from data to models to knowledge to DSS, and each of these aspects can be tackled in flood modeling and flood case. And today I am trying to show you some work that we have done with citizens' data and with inference and understanding from models and where these have been used. I selected two cases in China on Yellow River and on Huaihe River for decision support system, and then as an approach in one project that we had funded by European Union about the citizen science contribution to monitoring and flood modeling. And I will tell you just a few words about one ongoing project. There are several. There is Futural Restart-In, but depending on the time, I selected Futural to show you what we are doing nowadays for flood modeling using nature-based solutions. It's ongoing work, so we don't have many results. Starting with decision support, so I was looking at the previous presentations in preparing this one, and I was thinking that we, due to the nature of our institute, and we have students from all over the world, we always look at problems, at solutions, and if they have impact and what are the results. So that is how I structured the presentations, that for every case study and problem that I'm going to present, I'm trying to show you the problem that we are going to tackle and with whom we did it and where does it have impact. So the first one that I have selected, it's a case study that we have done actually several case studies on the Yellow River in China. And the main problem that we looked at there is how should hydropower producing reservoir be operated in case of an incoming extreme event. I don't know if you can see my mouse. I'm not sure. You cannot, yeah?
We can
Maybe I
see
will.
it. Yes, we can see you on it.
You can see it. Okay,
Yeah.
then, oh,
It's
that was
a
not
bit
my,
small, but it is still visible.
no, okay. Now I went out of it because of this pen and I don't want the pen.
Yes, no problem.
Okay. Okay. So there are several dams along the Yellow River, and immediately after one of the last dams, there is a region where with a lot of population and a lot of time flooding is happening, and all these dams are producing power, and they are most of the time when there is a high incoming flood hydrograph, they are flooding downstream due to the producing of power. So we were looking how to operate these dams, if possible, in such a way that the flood impact is reduced, and how to design a framework for operation. So the solution approach, and I will come in more detail to it, we were designing a surrogate model to determine the inference between the flood extent that it is happening in the downstream with respect to how the dams are operated. So actually, based on that and on the inference, we were proposing a framework on how these dams should be operated. So what we did, we operated these dams in different conditions, and we produced a flood hydrograph in the downstream, and then that flood hydrograph we routed on a 2D area in the downstream and received different flood extents and different volumes. And these were not enough because there are so many possibilities to route a flood. So based on that, we were building surrogate model. And for the surrogate, you can see here, we were really correlating the flood extent and the volume with how all these hydrographs were, all these dams were operated. So for the surrogate, we were looking and seeing what is the best way to operate backward. So in order to model the downstream flooding, we used Delft 3D discretization. The valley in itself, it's very interesting in the downstream because it's quite narrow, and a lot of the flood that it is happening, it is not behaving like through flows through the channel, and it is coming and not truly like a backwater, but also flowing back. And there were a lot of interesting phenomena happening, and we were trying to capture them with a model. And we were lucky to have some of the previous flood inundation extent that we could use for validation of the flood extent, and then we could produce different flood areas extent. So the result of it is that we have produced a correlation between the flood volume and the inundation area. And depending on the point that it is on this graph, we could look backwards how to operate the dams. All this was part of one MSc work of a student, and especially of a PhD work of a student who is currently working in the IT system of Yellow River, and many of his PhD research and what we have done are currently implemented at a much more better and refined way in the Yellow River Commission nowadays. So we are proud to have this impact. The next case study that I selected was the Huaihe River in China, which is also very interesting because it has a lot of storages along the river Huaihe. And in the most downstream part, it has an important city, the Bangbo city. And this city is usually flooded because these storage areas are not always used properly for flood protection. And what we were looking at is how should these storage areas along the river be filled with incoming flooding waters such that the city is protected. And the damages, what's most important is that we were looking on how to reduce the damages in the storage areas, because if there is no flood, these storage areas are used for agriculture, and also in the upper parts of the storage areas there are also houses. So the damage, if the flood comes, it's not only on the crops, but also on the houses. In the most upstream part of the river, there are a lot of fast flash floods, and then they go in the middle section and then the downstream. We were looking especially on the middle section, so the hydrograph from the downstream was provided to it. How we did that, we used a couple Heckras River model and an NSGA global optimization algorithm. But let me show you a bit more about the model itself. So there are several storage areas. This is the river in the 1D, this is a city, and there are main 4 storage areas that are operated in order to protect the city. So they, to give you an idea, is that these storage areas were used throughout time, except of one lake, to protect the city from from flooding and from other damages, but not always in the best way. And there is a lot of population in the lake, in the storage areas themselves. So it's not only agriculture, and there is also farming area there. So what we did, we tried with Heckras very conceptual in the solution approach modeling of 1D plus storage areas where only the volume and depending on the depth is represented. Then we were using a terrain-based storage area. So we were looking at storage area, really looking on how terrain is there. And then we also tried a 1D, 2D representation of the river and how these storage areas are operated. But very briefly, so you can see that the model has input, output, and it has connections with the storage areas conceptually for the 1D conceptual storage. We were looking at different ways of operating the gates that connect the river with the storage area. And we were looking when to open and close this gate in such a way that the storage area takes as much as possible from this volume. We were having 2 objective functions. I will show you in a moment. Apart from this testing with 1D storage area model, we were also looking at storage areas in more detail if they are terrain-based elevations. So we were going to a lot of detail for the storage area. And as I said, we were also looking at the 2D area where we had to look much more on the gates were becoming actually how they are operated, boundary conditions to our 2D flood model. So when the storage areas become 2D flood models. So we had 2 objective functions that we were looking at on how to reduce the downstream flood risk to protect the Bangbu city by operating the gates. So we were looking at the warning level in the Bangbu city and how to operate. Our decision variables were the gates operation. And then the second objective was to actually reduce the damage in the flood storage areas. We were trying not to have a big damage in this storage area. So we were doing model-based optimization by determining the storage areas, gate operation, with decision variables as a gate operation. Well, this is very schematic how we were coupling this Heckras model with an optimization and how we were with an NSDA and how we were running it many times. And for the damages, we were looking cell by cell in 2D areas, for example, and inside each grid cells, all variables and parameters are the same, but we were looking at the flood, at the land use information, if there are houses or not. So all these were computed cell by cell. And the result of it is that we were running, as you can see, all three cases, and we were running the optimization for these two objective functions, the downstream flood risk and the inundation damage. And we were obtaining slightly different results. I will come back to it. Actually, the conceptual LAM model was very different very different. It was different in results from the terrain storage areas and 2D mesh areas. And because of that, we considered that these last two, the 2D and the terrain representation of the storage areas, are much more better. So after selecting these, we were looking into possible operation strategies. We actually have a chapter about all this work last year in advances in hydroinformatics. And just to give you some examples, so if we select for the downstream risk, how to operate, we were able to obtain how to operate the gates in each of the lakes, and we were actually obtaining a hydrograph reduction in Bangbu City exactly at the peak. So here at the peak, we obtained a reduction of the hydrograph looking into that. What we also looked, because I also put how does the flood extent look into the three cases, you can see that actually the conceptual 1D storage area, when the storage area is truly conceptual, not terrain-based, it's very different from the other two. So the other two are much more better representing the flooding, and also they are running much more faster. So we were looking at these two cases. That was the work done with Chinese MSc students within a memorandum of understanding with Huaihe River Commission, and how they are taking this and using it further. That we don't know exactly, but that are the results that the students find out, and they were very happy to be of support to Huaihe River Commission. With that, I'm going to the second part on the critical importance of citizen data. So we many times are faced with data that is not enough for the local authorities, and it is collected with in an expensive way. All the decision makers and experts do know how to get this data, but sometimes citizens can add a lot of value to it, and we were exploring if citizen observatories can add value to traditional data acquisition. And we were not looking into the citizen or organizing the citizen, but how the collected data is useful or not. And we had test the cases in two different case studies. One is in a very heavy urbanized area and in a delta, where flood is not a hazard, where flood is a service, and it is very important to look at the water levels for the flood. This all is done in a project for which the project is finished, but you can see the link to the project and to the results. The rural wetland area is in Danube Delta. It's a huge area with an integrated network of canals and small lakes in Romania. And the other urban area is a catchment in Greece, just upstream of the city of Athens, where the main problem is that many times the canals are blocked with different debris, and they are not functioning really very well. And citizens could report what is happening there, and then immediately the models can be improved. So what we did as a solution approach, the project was much more with many partners. It was funded by European Union. There was one partner specialist in mobile application that developed 4 apps exploring, collaborating, and measure, which citizens could put on their phones, and as soon as they go on the field, they can measure. And like that, the citizens become the eyes for the decision makers. And we were looking if such collected data like water depths and velocities can improve the models. And then based on that, if we can analyze mitigation strategies because the models are improved. What we used for that, we used physically based models and also hydrodynamic models for the network in Athens. It was challenging to collect all this data. We had to design campaigns to measure stage and velocities and also discharge, and we had to determine where the authorities do not have enough data. Here, for example, it is the rural case study, huge wetland within the Danube Delta, where there are points of collecting the data, and where it is very important to have water on the canals, and there were many canals when sometimes there is no water, and the authorities would like to know where to go. I just want, as a side thing, to mention that it is very difficult to convince the citizens to collect the data. But in this particular case, the ones that were involved into collecting data were bird watchers, and there were many areas in the delta they were not allowed usually to go and to do photos of the birds. And because of the project and because of testing collection of data, they were allowed to go in those areas. So they are very much interested to collect data, and they used all these apps and they collected data. In order to collect data in such an area, we had to design paths, how to reach those areas. We had to go by boat because these bird watchers are going by boat. And we were determining where to collect this data and where to put the boats on both sides of the canals. And I don't know how much visible it is. This is how the app looked on the phone, and every user could decide what they want to measure, velocity or water level. And based on this measurement, and on the campaigns, we rerun the model, and we had different boundary conditions, upstream and downstream, depending on the campaign. I even have modeling of the flood. It is a service there. And we could improve the cross sections based on the modeled water depth and on velocity. And these are the results that we have obtained. That we have seen that sometimes what authorities have measured cross section is good and is well determined by the crowdsourced data. But sometimes the measures that they have of some of the canals is they have in the model, and based on what they measure, it's quite wide as opposed to what exists in reality. And the measurements that we were doing during the campaigns with ADCP data just to corroborate with what citizens are collecting showed that the citizens are collecting good data. And then the whole model was corrected with this new cross-section. And here are different measurements on different canals in the data. And that showed that it is a good approach to improve the modeling. if I come to the urban case, in the city of Athens, the canals are quite well determined. So what we have developed is a phone application that from different photos from the riverbank, we could reconstruct the cross-section. So a person goes with a phone on a riverbank and starts taking different photos of the riverbank in many positions. And then it tries to capture different position and also to have an overlap. We were looking what is happening if there is a bridge. And then with the data, we were trying in three particular, here what I'm showing you in three particular points along the river, along the canal within the city of Athens, how well the side view that is from the phone is showing the cross-section as compared with this dotted gray line is the original cross-section. And though some two cross-sections were very well represented, one was really far from the reality. There is a possibility to improve. It shows that when there are areas without data, such methods can be applied with success. And the results of this project and the impact was that we really had possibilities to design new path routes. There is a improvement of the model with all this data. And that is a PhD work of Taina Assumpção that will be defended later this year. And the other thing is that actually the local authorities are using the way to collect data. They are calling for citizens from time to time to use these apps to collect data because they started to build trust in this type of data collection. And just very, I hope I'm still in time, very a new project that we started. It's about innovative solutions for rural areas. That we are looking on how nature-based solution can improve or the effect of can reduce the incoming hydrograph or can keep water into a catchment in case of droughts. And for that, we just started. We looked at a nature-based solution. We started on how to represent this in models. The project itself, it looks at KPIs for droughts and floods after the modeling and usage of nature-based solution is implemented. And it has as an aim to produce an online platform that will inform the rural areas what are the possibilities. We have two case studies. One is in Belgium, which uses a very complex physically based distributed model, which is very hungry of data, but where there are a lot of floods, and we are trying to see if certain nature-based solution representations in the catchment can reduce, can mitigate the effect of floods. And then we have an area, a very small area in rural area in Romania, where there are several villages that are extracting drinking water from the underground. And when there are floods, all these wells are flooded, and they would like to avoid that wells are flooded. The main challenge is how to represent, because all these models, hydrological, hydrodynamic models, do not have a way to represent nature-based solution. You have to look at the parameters and which parameters will best represent a certain nature-based solution. So we are looking at the possibilities and design of nature-based solution, taking into account what is implemented in such a model. So I'm coming towards the end of the presentation, because what I try to say is that each context is local and has its own complexity. Each flood modeling was very different and presents unique challenges. Each one has a different case study and problem to be solved. And all this has to be tailored to solutions that are feasible locally. And we all need to understand specific geographical and social context in order to solve this. The second one about citizen availability, about data integration, I think that the citizen science provides valuable insights and local insights. The most challenging, which I did not present here, is the quality of data that comes from this collection. We had to look at all this data. Not everything is good from what the citizens are collecting, and some has to be sorted out. But the main aim was to show you how to be used in modeling. And our outcomes are saying that traditional modeling approaches and the citizen source data enhances the model accuracy. And then the last part with a nature-based solution, we are still in the initial phase. We do have challenges in representing these in flood models, and it really requires integration of specialized modeling approach. And with that, I have finished my talk, and thank you. And these are the details of for connecting, and I will be happy to answer to any questions if there are questions. Thank you.
Thank you, Ioana. Impressive. Great presentation. Thank you very much.
Thank you.
Is there any questions for Ioana? Yes, Albert. You can unmute yourself and ask your question directly.
Can you hear me?
Yes.
Yes. Yes.
Okay, wonderful. Thank you so much for your presentation, Anna. That was great. I got a question about the involvement of citizen science in your projects, and mainly regarding the apps. I've a little bit experience with apps myself, and it's not straightforward to one, develop them, and then also to make them such that people understand how to handle them. But that's not only that's only one part. There's also connectivity, and I saw you encouraged people to, for example, take measurements on the Danube Delta, I think.
Yes.
For example, depth or velocity measurements. Can you explain a little bit better maybe how many people in the end contributed data, but also if throughout the Danube Delta, is there connectivity? Is there how do you say that? Is there cell connection with the cell phone? And if not, did the app kind of capture the data, but then later on transmit it or something like that? How did you overcome that?
Yeah, indeed. The connectivity was very good, but even though the connectivity is very good, the app is designed in such a way that all the data collected is stored locally, and when the citizen who collects data considers that he or she has enough images, then it connects to a special platform and provides the data to the, so there is a collect, collaborate, I can go, so there are, it's not only the app on the phone itself, but it's also the platform to which they connect to provide all this data. Of course, it can be provided one by one, and there was a good connectivity, but it is better if it is provided, everything that is collected in one go to that platform at a later stage. They can decide at what hour, when, and everything will be downloaded from their phone and then also deleted, so such that the phone is not overloaded. We had for each campaign around 50 people, so we did 6 campaigns, 3 per year. So we had quite a lot of people contributing, but they are not randomly going. They were organized campaigns.
Got you. Okay, wonderful. Thank you so much for the explanation.
Yeah, great. Thank you, Tristan. Yes.
Yeah, lots of very interesting work. I also have a question about the citizen science part. I mean, there are, of course, different groups now who try to develop ways to bring citizen science in it. So I know had a lot of interaction with Jan Seibert and his group, which doing something similar.
Yeah.
Is there any kind of sort of effort to connect all of that? Because ultimately, you know, there's interest in creating larger data sets, and there might be opportunity for developing, I don't know, a common database where all of this gets connected and combined or something like that.
Well, at the time when the project was funded, there were 4 sister projects that were running in parallel, and they were all under one umbrella that was called We Observed. And it was in the second phase of citizens' observation data. There is, for We Observe, for the umbrella project to bring everyone together, there was an effort to bring and to create databases. But these are very specialized databases because some data is about soil moistures, other data is about depths in the river for a specific location, like for the Danube Delta or for the Kifissos River in Athens. So they are very specific. We were always advocating for the data to be available and free, but some of the data that goes to this special form platform, some authorities are saying that they are proprietary and they can be accessed if an email is sent to them, and then they will provide access for downloading. So there are some hiccups there, but in principle, they are free and they have to be free, but they have to be asked to provide this data.
Great.
Yeah.
Great. Thank you, Ioana and Tristan, for a nice question. Juan, you have a question. Could you ask quickly, please? Because we have to go with your presentation next. Yes, go ahead, Juan. Can you hear me, Juan? We can't hear you, Juan. Are you there? Okay. Till he gets prepared, then maybe he gets an issue. Yes, you can hear us?
Well,
Juan, if you hear us, please go ahead and ask your question. We can't hear you. So, Yuan, I have a quick question.
yes,
back.
please.
So that would be great to put all your modeling part to an AI-driven system. Have you guys looked into it, or have plan to have such a study?
Well, but the surrogate model is a kind of AI driven, because if you do a surrogate model, you provide all the data and you decide the variables on which the surrogate will function, and then all the rest is produced by the surrogate model in between. So it is a kind of AI system.
Great.
Yeah.
Great. Wonderful. Juan, can you hear us? Juan, are you there? Can you share your screen, please? Because we don't have time. Thank you, Ioana, for your presentation.
Yes, you're very welcome. And
yes, very nice.
any time later, I can answer.
That's great. That's great. Wonderful, wonderful job. So hopefully Juan can get connected.
Can I ask something?
Yes,
What?
if you can ask very quick.
Yes. Professor Joanna, how are you doing? Nice to see you again. Thank you for
Nice to see you.
Let me take a quick question. I'm very inspired by this citizen science. I'm from Colombia, and here we have a lack of access to information. So this is a very useful way to have information in our projects. My question is more regarding what are your insights for this kind of citizen science approach to live beyond the project? How can we encourage people to keep collecting data beyond the lifespan of a project?
Well, we were trying to test that for beyond the lifespan of a project. So if there is a win-win for those collecting data, they will collect it. Like I was saying, the bird watchers were very much interested to collect data, and they are interested to still collecting data because they are going into the delta anyhow. And then if they are allowed to go in areas where birds are located, they are interested. So there is a win for them because they are going into that area. Local people might be inspired if you do a bit of campaigns of awareness, how the data collected by them will be used and how that will help reducing the floods, and they will be very happy to provide and to collect continuously such data. In the city of Athens, when the citizens have seen that with a very simple app, they can show that the canal is blocked because a car fell into the canal, or there are other debris. And that will protect the houses that are in the upstream. So the people in those areas were very open to still collect data. So there should be something for those collecting data. That is how you maintain this ongoing.
Great. Thank you, Joanna.
You're
Let's see if Juan can present his work. Juan, can you hear us? You're muted, Juan. Can you hear us? Okay. It seems we cannot hear
Nope.
you, Juan.
Hello.
Hello? Yes, we can hear you now. Are you ready?
Oh, that's great. Yes, sorry, everyone.
Can you wrap up
I
in 10 minutes, Juan? Thank you very much. Because
okay.
yes, sorry.
Yeah, now everyone hear me, right?
Yes.
Okay, great. I'd like to give some update for the flood map project. For those for those are new to the discussion, I would like just quickly overview the objective of the flood multimodal in the comparison project here. The objective is to assess and compare the long-term flood simulation and short-term range flood forecasts, so that allow us to understand, to enhance the understanding of mechanisms and identify uncertainties and increase confidence of flood risk assessment. So the whole idea is that we evaluate multiple models with the same data sets for this project, and with the hope to finally to transfer these results to application, and in particular for the Global South area. So the last time I overviewed some candidate hydrologic models and for these proposals. And today I'm going to share some updates on the study area choices. And we are moving slowly, but we do move a little bit. So for this project, we we'd like to start from the Kansas area with more focus on the Mississippi River basin. The main reasons to make these choices is the first one is that the data availability and the quality of the Kansas, and also in this area, most of the candidate hydrologic models has a lot of historical simulations and retrospective research over this area. And for example, the right side is from the dry model that my group developed. And this show one of the snapshot of a real-time flood forecasting in the over the Kansas, and showing the real-time validation results at back to 10 years ago. And the flood system is still steadily online, and this is one of the candidates. And moreover, the Mississippi River also allows us to look at a larger variation of temporal and spatial variations in the hydroclimate characteristics, and from the upstream to downstream areas, and also allow the more opportunity to look into specific river basins with or without intensive human intervention. So that's the main reasons we are picking this area. And for example, here shows the Iowa Cedar River Basin. Here, this is a river basin located in the Central America, United States, with relatively simple hydrographic elevation variations, and it's considered an area to relatively easier to study. But later on, I would like to say, even in such area with very relative simple landscape, but there's still a lot of challenges. The first challenge for the multimodal intercomparison activity or studies is the uncertainty in the precipitation. Here just show us example that for this Iowa River Basin, the different precipitation products shows a huge difference, even at like a mean annual scale. If you look into the daily or monthly and seasonal, they are more the larger uncertainty. So this is kind of the issue we first to tackle. And with this huge difference in the precipitation products, we can see the hydrologic modeling can give you a large difference of the streamflow simulations. The right side shows the Nash coefficients at different locations with observed USGS data, and but driven by different precipitation products. So the right side is a hydrograph, but here the question is, which precipitation product represents the best or closest to the truth? It's really hard to tell. Even sometimes we cannot really just simply based on the Nash coefficient or relative bias, but these are things we need to look at it. So given that we don't know the truth of the reference precipitation, our strategy is to first look at mean annual precipitation products, as this is this gives us the more confidence based on the mean multiple year mean annual observed stream flow and evapotranspiration. If you look at the tables, the first column, the reference call here, we use actually is calculated at the real basin scale using the observed stream flow and the modus 16 product, ET product, and give us a reference. Remember that this is just the reference at a mean annual level. But if we believe that represents the close to the truth to calculate the bias of different precipitation, you give this the bias on the top row here. And if you look at down the monthly Nash coefficient and the mean annual relative error here, it clearly gives us that the larger bias in the annual precipitation, the larger uncertainty or bias errors in the simulated stream flow. This is the kind of an important logic for us to design the flood map experiments. So I would spend some time on this framework, which we are still working on yet. So the major part of this framework is that we critically, the first step is to derive the best estimation of the precipitation for a given catchment or basin, river basin. Our strategy is top-down, first from the mean annual scale, and then down to the seasonal, monthly, or event level scales. But the main logic is that we based on the water balance equation in the middle here, and relying on the different multiple source observations from the for the discharge and the multiple satellite-based ET and soil moisture, assuming the storage change, the delta S in this equation at annual scale is negligible. So we got the reference precipitation. That's the first step, and then we use that for the second part is to evaluate the P and the Q bias relationship. With that, we derive the best estimation of precipitation. However, we go to a further step. We explore the second further validation of the precipitation evaluation based on the models calibration. We on the basis that given the good quality of precipitation and a reasonable hydrologic model, the calibration and validation period should have a consistent model performance with the same model optimized parameters. That's the main logic. So with that done, we can derive a coherent water budget and a different water component for comparison element by element among the different hydrologic models. So that's our plan for the next step. So we are still in the preparation stages and working on this framework. And if anyone has suggestions and comments, are extremely welcome. But here I would wrap up that this project, the flood map project, besides the different models and their uncertainties, and the precipitation uncertainty is our first concern, and try to tackle this problem and try all the best to get the best estimation of the precipitation at the catchment level and sub-catchment level as best as we can. So that's the point here. Okay, I would stop here. If there are any questions, there's 3 minutes left.
Yes. Is there any quick question for Juan? Albert, can you ask your question quickly, please? Thank you.
Yes, thank you. Thank you, Juan, for your presentation. I see you use mostly satellite products for to capture the precipitation on different timescales. Are you ingesting maybe also some observed from local radar stations or something like that precipitation to see how well? I didn't capture that. Maybe you talked about that, but go ahead.
Oh yeah, yeah. Actually, the stage 4 and they are like Q2 are radar project, and this NLS2 is considered as the best estimation, the kind of operative product. We are looking into different precipitation products from not just satellite, but also satellite, radar, rain gauge, merged products. But IOR is a very simple area, easy area we are considered, but still has a lot of challenge here. But our goal is to in those ungauged areas that's more challenging, but we still need to working out a way to addressing the precipitation quality first before we dive into the model calibration and in the comparison.
Yep. No, that makes sense. Okay, thank you for your explanation.
Yeah, great, thank you. Great job, Juan. Thank you, very impressive. Remote sensing is slightly outside of my expertise, but I really enjoy your presentation. Great work. Thank you very much. And thank you all for joining us today. We do not have our monthly meeting next month. We'll be at GHP meeting. And I want to thank our presenter today for presenting nice kind of the research work here. Thank you all, and I hope you have a great weekend.
You too, and thank you.
Bye, Yuan.